Nice being with us today. We are moving to the second phase of the event, Qiskit for Fed. So today we'll be working with the second notebook, which is really talking about the bill states. So before we even go far and go more details, I want us to talk about what we understand, how Bell State is being used. What is Bell State? What can Bell State do? So before I now even put us through the process or the steps of writing the Bell State code. So in quantum computing, Bell State as specialized or specific quantum state is a quantum state of 2 qubits. So you can be given 1 qubit, you can be given 2 qubits, you can be given 3 qubits, up to 129 or so qubits can be given to us. But if you are working out with a Bell state, you are making use of 2 qubits, which represent the simplest examples of minimum entanglement. So these states are crucial for quantum information quantum information process tasks such as quantum teleportation, super density coding, and key distribution. So this true area of quantum, you make sure we make use of Bell state, the quantum teleportation, the work of teleportation. You can communicate from here, you can teleport, you can send the data from here to another place. Talk of dense super density coding and key distribution. So there are four Bell states, and these four Bell states we have them the one of 0 or 1 minus 1. This we have them in phi, we have them in beta, we have the phi positive, phi negative, we have the um we have we have the sorry we have the phi positive, we have the phi negative, we have the alpha or theta positive and negative. It depends on the way you want to use it. So those are the areas of it, and each of these Bell states changes. Whereby you can have the phi positive can be 1 over root 2 open bracket, where we have the curve bracket, which is 0 0 plus 1 1, which is in curve bracket also. In in uh, in in quantum computing, there is what we call Ket and Bra. In protocol, is a representation of of quantum computing or quantum computer. Sorry, quantum computing, whereby we have your qubit inside. It's just like a bracket that is holding your qubits, where you can have 0 0 0 1 1 1 and so on. So those are the superposition aspects that of the Bell state that we'll be looking at. And from there, let me just share my screen and let us write some code. Share my screen. So please, anytime you open your collab, please do not forget to install. You will need to install your Qiskit again every day. You open it, you install your Qiskit every day, every time or anytime you open it. You just have to
Uh,
install it. Sorry.
Steven, sorry to interrupt. Your screen is not visible.
Okay, you want to say
Your
something?
screen is not.
I'm with
Screen
you.
is not visible.
Please, can you speak louder? Can you hear you clearly?
Screen is not visible yet.
Okay, my screen is still going to come up, please. It's still going to come up.
No.
Sorry about that. Please, can you see my screen?
Yes, it is visible now.
Okay, thank you so much. So, okay, let me just move to it here. So from there, sorry, I will just copy and paste the necessary library I need to install. Um, okay, sorry, this is not the one I'm supposed to. So this collab. So from there, okay, let me first install this. So any of these collab page that you open, you need to install them. So that's it's running already. Okay. So if I'm going to run any code here tomorrow, I will still need to reinstall it because it's in the cloud base. Okay, let me eat that. Let me run the second one. Okay, still loading. Okay, we are done here. So let me run the second one. Okay, so it's still installing already. Okay, successful. Okay, good. So in it's still loading. So it may take some time. Let me just do that. Okay, so that's Bell State. So in Bell State, I'm looking at the um rocket socket overview. Socket overview. There are some important things we need to know. For us to create a Bell state, there are some important things we need to follow. So in that area, I would love to list them out. So the first one is the first one is you start with 2 QB in the initial state. The initial state, maybe we have sorry, okay, 0. So this is what I call cat. This cat. So we have we start with 2 sorry, we start with 2 qubits in the initial state of 00 qubit. Oh, sorry, 00. So the 2 qubits is either because you are going to count, you'll be counting it from the array. So it's not just that you just write one or two. I'll show us that. Let me just give us the overview first. The second one is apply and Adamon gate. Which is H. We call it Adamon gate. You keep seeing this every time, Adamon gate. Actually, we're supposed to talk about the types of gates that we have. Adamon gates, the qubit, um, Adamon gate to the qubit, Adamon gate to the qubit. Sorry, Adamon gate. So that's when you first apply the two. You have the two qubits. The next step is you apply Adamon gate to the qubit, to the first qubit or to the second qubit. So here you apply a C not gate, which will be uh on the first qubit, which will be on the first qubit. We are going to now you can see we have already used the first gate and another gate, which is called synod gate. The first one is Adamon gate, which will be applied to the first qubit, and also this synod has two should I call it two legs. So when you are calling it, the initial will be on 0, and the um, other part will be on the first cube, on the first qubit, on the first qubit. I'm sorry, okay, on the first qubit. Sorry for that, please. On the first qubit. Uh, okay, the fourth one, which will be apply is Z. Sorry, is Z gate. Apply Z gate or or poly Z gate, poly Z gate to the second qubit, to the second qubit. So 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 these are what we look at when you want to create your Bell state. Even if you want to create the algorithm, there are some algorithms that you work with. All those algorithms have steps. You just don't create any of them. You follow the step. Okay, this is the step I need to follow for the first part, for the second part, for the third part. So before you start adding other necessary things to it. So from the let's just start with the code. So QC is equal to, please, if I may ask, please, I don't know if you can hear me. This QC is a variable. Do you have the knowledge of Python? Do you know how to create variable? You have been asked us. Do we? Okay, if we do this, this will be a yes, thank you very much. Yes, okay, good. So now I'm creating a variable that is going to hold my what? My socket, my Python, sorry, my quantum socket. So we have I have quantum socket. Now, after I build this, after I wrote this, I given it 2 qubits. Now, you can be given a question that make use of 4 qubits in this research, in this structure of a code or anything. They are giving you 2 or 4 qubits or 5 qubits. When you are calling that, you state your how many qubits you want to use. Is it 1 qubit? Is it 2? Is it 3? Now I'm stating, because we are working with what Bell state, which we have to apply just only 2 qubits. Now I'm stating that okay, I'm making use of what 2 qubits, and the next state is what state. Okay, now looking at the overview here, the circuit, this state with 2 qubits in the initial state. Okay, now we want to add the second step is add an Adamon gate to it. So you're adding an Adamon gate whereby you call your variable, and our variable here is qc dot h, open a bracket. That bracket means you which of the port, which of the socket, sorry for using that, is wrong. Which of the socket is or which of the qubit is the first qubit or second qubit? Which actually you're not going to write one for that, because it's just like an array. You have a set of numbers or a set of orange, and they ask you to list the array number. The array start from 0, 0, 1, 2, 3. So now this one will be 0. It's going to be 0. And the second one is what? The C naught. C naught is taking 2 options. where we have C. When you are writing your C notes, you make use of CX. You don't write single. So please take note of that. So from there, it's taking two option, which is two of the gates. We have the zero, that's the first gate, and the second gate, sorry, first qubit and the second qubit, which is one. Please don't be confused with this. Why you are saying it? Why this is the gate we are working with? Normally, I'm supposed to start with one, two, but in an array, we start counting from zero and one. You continue to three, you continue to four, and so on. So that's that. So here now, you move on to C naught, which we are creating our Z gate dot Z, which is 0, and that Z gate is going to be on the first on the second qubit, sorry, on the second qubit, which is 1. So let's try and draw that. Okay, QC, that's draw. QC dot draw, which is let me try and run. I'm having an error. Sorry. Okay, sorry about that. I did not for one of. Okay, see, it should be okay. Okay, okay. That object is not called. Sorry, please. I'm just having a little error. Sorry, please. I need to check for the importation. So this is how you go through it. When you have the documentation. From there, you can just check where the error is coming from. Your maybe where you make a mistake. Okay, okay. Sorry, I'm sorry about that. I mix this for okay. I means rearrange. So sorry. Okay, it's not drawing it. Uh, uh, okay, thank you. Okay, so please let me explain myself clearly in this aspect. Let me explain. Actually, some of my bosses are here, but let me explain myself. In any we call it library. In any aspect of a code that you're writing, you must add a library to it. You must add a library to it, and from there, you can call the library. So instead of me writing all the code, I will call the library. So this is the library, which is from Qiskit import quantum socket. So that's how this part will able to work. So please okay, please give me some minutes, please. Mr. Aneka,
Hello,
Mr.
good evening.
Aneka, good evening. Please, can you take a floor for now, please? I need to set something.
Okay, I am not joining with my PC at the moment, so to be an issue right now.
Please just engage them with something. Just explain. Um, just you can just explain those any stuff to them. Just give me 2 minutes.
Okay, no problem. I hope you come back soon. Okay, so good evening, everyone. I just joined the meeting. Kenneth, Mr. Kenneth, good evening. Good evening, everyone. Once again. So we're talking about why I saw there were Bell states, and Bell states are fundamental states that are used as should I say structures, basic fundamental structures to design many quantum algorithms. So Bell states starts with a Hadamard on the topmost qubit, and the Hadamard would now be split with a C naught to the remaining qubits. So once you have that position of a Hadamard and a C naught, you have what we call a Bell state. And this Bell state is useful in quantum teleportation, is useful in many communication circuits and many other implementations. So let me look at some advantages of Bell state.
Sorry. Thank you so much. I'm really sorry something came up. Actually, where I am, I need to attend to some things. So sorry about that. Mr. Aneka, thank you so much. From there, please, let me just introduce some of our members again. Mr. Aneka is a member of Q World and a Q Nigeria. And also we have the president of Q Nigeria here, which is Mr. Kenneth. He's the president of Q Nigeria, and is the one that is going to be taking us through the second notebook of today. So before I hand over to him, let me try to explain where I stop. Please try to thank God this issue happened. If you check most of the sorry, I'm not showing my screen. I'm so sorry. Yes, I need to present back. Okay, if you can see the error message that I got the other time, because what I did the first time was I wrote Qiskit actually. So some libraries are being written that way. Qiskit okay, sorry, I did import Qiskit from, and I wrote quantum socket, but which was wrong. And okay, I was mixing it up. So the next thing is I moved to the what, to the documentation. You can see does dot quantum.ibm. So we have the documentation. You can go through the documentation. You can see actually this one was for Bell State as well. Thank God. So you can see the following code is for what, is for the Bell States. So the way you can create your Bell States and so on. So for my side here, this is how it is for Bell State. And I state what the overview of the Bell State for us. So today we are still going to the person that is going to take you, Mr. Kenneth, will still take you through the necessary part of what you need under this notebook. So I will be so happy to call and Mr. Mr. Kenneth, can you hear me?
Yes, I can. Yes, I can.
Okay,
Thanks for yeah, thanks for taking or handling things thus far. Um, yes, give me a second. Let me set up and share my screen.
okay, thank you so much. Thank you. So Mr. Aneka was trying to explain the advantage of Bell States. So it's okay. Let me just go through some stuff here. Um, if any of us are having issue with the first exercise that the first notebook, please you can. Oh, thank you, Mr. Paul. Thank you so much. I did not even see your message. Thank you. So it was correcting me. So please let us go through this. We can use this to answer the first part of the question. So please try and go through it. And the first part of the exercise that is given to us. And also, I think you can still apply some of the process here to the second exercise. So that's part of that. And I don't know if any of us that are here presently. IBM is taking internship um for quantum researchers. So if you are interested, please feel free to check online on IBM Quantum. Just type IBM Quantum Internship 2024 or 2025. So type it on Google, and from there you can move ahead to apply. And if any of these come up again, we're going to keep letting us to know. So we are still waiting for our instructor today. So he's going to be taking us through the second part of our Qiskit for first notebook. So whereby he's going to be telling us about how to create and draw a singlet of qubit state sockets, how to run it, and also how to create a W state socket. You can see how many states how many different kind of socket that we will be creating, and also talk of many other parts of the necessary things that we need. And also you look into the exercise, and if you have any error, any issues, if you are stuck, please feel free to check what the documentation. So it's already sharing the screen. So Mr. Kenneth is going to take the floor.
Okay, I should start now.
Yes, sir.
Okay, no problem. Okay, thanks a lot, Shegun. So hello everyone. I am Kenneth Isamadi, and today I will be going over the second notebook for the Qiskit for first challenge. Okay, so today we're going to be looking a bit. We're going to take a look at states like once more, and then we'll work on creating a Bell state circuit. We'll make use of our sampler. We'll also create a W state circuit, and finally we'll look into VQE, the variational quantum eigensolver. Okay, so let's begin. Okay, so the first part of the notebook is to carry out all the necessary installations. So you handle these parts, and the next thing would be to insert. So if you should have been provided with a token from IBM, So I think this helps you, or this will enable you to use one of the quantum computers in the cloud. So you provide that here, and finally you can start working on your circuits. So the first part here, we import NumPy, and okay, let me not just run over everything here. The most important things, which you've definitely seen, you need to import the quantum circuits, and you have a few tools here. So with state vector, we can visualize our quantum states. We also have operators here. It enables us to make use of a couple of operators. And we also have our samplers and a couple of other things. So the first, okay. The first task we have here is to create our belt state circuit. So there's some side notes here, and we're told we have a box that contains 2 chocolate candies, vanilla and raspberry, and we're to build a quantum circuit that has an equal probability of getting the vanilla or raspberry flavors. Okay, so we need a circuit that has 2 states. Sorry, I don't know, is my background noisy? Am I audible?
You're audible. You're audible. It's not
Okay, okay.
noisy. You're audible.
Okay, perfect. So we have 2 states we're supposed to create, and the states are meant to have equal probabilities of being selected when we measure. So you could actually think of the box of chocolate candies. Okay, so the box of, we have a box with 2 chocolate candies. That's the vanilla and the raspberry. And so we've not really looked into the box. We just know we have a box, and someone can like put their hand in the box and pick one of the candies. So the act of you picking one of the candies is measurement, and there's an equal probability. Since we have just 2 candies, that's the vanilla and the raspberry, there's an equal probability of picking either one of them. So what we're going to do with our circuits is that we're going to create these 2 states, 0, 1, and 1, 0, with an equal probability. And when we measure, we're going to get either one of them. And you can think of that as like putting your hand in the box to pick the candy. Okay, so we have, okay, so this is the exercise here. So we've earlier we learned about belt states and EPR pairs. So this is so you can read this. They are entangled and normalized. And okay, now we're going to move on to building our circuits. So okay. The first thing we're going to do is to request for 2 qubits here. So we have 2 qubits, and then we're to build EPR pairs. Okay, so the first gate that we're going to need to apply is the Hadamard gate. I don't know, I think the steps were written out here. Okay, they aren't written out here. Okay, so let's say QCH. So we're going to apply the Hadamard gate to the first qubit. Next, we're going to apply the controlled NOT operator. So the Hadamard gate, it creates an equal superposition. So we what this does is that, okay, so initially when we start with our circuits, we start off with 0. Okay, so this is what I'm writing out here. Let me even give more space so it's clearer. So we start off with the 0 state, but when we apply the Hadamard, so I'm applying the Hadamard operator to the 0 states, what I'm going to get is an equal what I'm going to get is a superposition of two possible states. That would be 0 and 1. So now we have an equal probability of getting 0 and 1. So when I apply the Hadamard gate to the 0 state, this is what we get. Or let me write 0 first. 0 is usually written first. So this is the state we now get. And what's in front here, it's called the amplitude. And the amplitude works such that if you are to square the value here, you get the probability. So here I have 1 over root 2. And if I was to square this, I'll get 1 over 2. That means the probability that if I was to measure this state, the probability that I get 0 will be 1 over 2. And same here. If I was to square this, I also get 1 over 2. That would mean the probability that I get 1 if I was to measure is 1 over 2. So that's why we're introducing the Hadamard gate here. So we're going to apply it to the first qubit. Because we said we're making use of 2 qubits. We're making use of 2 qubits. Okay, so for the first qubit, we're going to apply the Hadamard gate. Then next up, we can make use of the controlled X gates. So here, we're going to set it such that 0, or the qubit allocation, 0 is the control, and this is the target. So the CX or C0 gate works such that, I'm sorry, the CX gate works such that if the control is 0, we'll do nothing to the target. And if the control is 1, we're going to flip the value of the target. So this is going to look something like, initially, we're starting off with, okay, so we're applying CX, and we're applying CX to, this is just notation. So I'm trying to say this is the CX, and we're applying it to the state, let's say the state 0, 0. We're going to get 0, 0. Because here the control is 0 and the control is 0, so we'll do nothing to the target. But in the case that we're applying CX to, let's say 0, 1, okay, nothing happens here also. So I'll also get 0, 1. In the case we're applying CX to 1, 0, we're going to get 1, 1. So here, our first qubit has a value of 1. So we're going to fit the second value here. So it becomes 1, 1. And in the case whereby we have 1, 1, we're going to get 1, 0. So everything depends on the value of the control. If the value of the control is 0, nothing happens to the target. But if the value is 1, then we flip the target. So here we flipped 0 to 1, and here we flipped 1 to 0. And that's because the control is 1. So previously, we showed something like this, where we applied the Hadamard gate to the first qubit, and this is what we got. But I'm going to introduce the second qubit at this point. So maybe I'll write my operator something like this. I'm trying to say H we applied to the first qubit here, and this is the identity. We're going to do nothing to the second qubit. So in this case, we're going to have 0, 0, and 1, 0. So this is where we're currently at after we've applied H to the first qubit. So I applied H to the first qubit. That's why it's in the superposition 0 and 1. And for the second qubit here, we did nothing. We just applied the identity. So it stayed the same. So at this point, we can apply our CNOT operator. So here, we apply our CNOT operator. And so we're applying our CNOT operator to this. And we're going to get something of this form. So now we get, okay, so here the control is 0, so we'll do nothing to the target. And in the other case, because our control is 1, we'll flip the target. So after applying CX, this is what we get. Okay, so for the states that we're trying to create, okay, we're looking for 0, 1 and 1, 0, but currently we're at 0, 0 and 1, 1. So okay, so we can apply another gate. Okay, so let's say we were to apply sorry, let me look at, okay, we're creating this is psi minus, the psi minus state. So because there's a minus sign here, we're meant to introduce a negative sign. So we're meant to flip the positive sign here to a negative value. So what we're going to do is that we're going to apply the Z gates. Okay. So we're going to apply the Z gates to the first qubits, and we're going to apply the Z gate to the first qubit and do nothing to the second. So at this point, okay, so we're here. Yeah, sorry. Like if I could annotate, this would have been simpler to write. Well, I hope it's clear. So now we're going to do this. So here, when we apply Z to 0, nothing happens. So if you apply the Z gate to 0, nothing happens. But if you're to apply to 1, you get a negative sign. So at this point, we're going to get a negative sign. So here, okay then. So now we've converted our plus to minus because we're trying to create the psi minus states. And the final thing that we're going to do at this point is to, okay, so now we can flip the value. So here we have 0, 1 and 1, 0. So we need the 0 here to become 1, and we need the 1 here to become 0. So that's what we're going to do. We're going to apply, okay, so an identity, we're going to apply identity to the first qubit and X to the second. So we'll do nothing to the first. We want it to stay the same. But we're going to apply an X to the second qubit. So let me just rewrite what we currently have. So this is what we currently have. And at this point, we're going to get, so now we're applying identity to the first, so it stays the same, but we're applying X to the second qubit, so it becomes a 1. Okay, so the minus stays the same. And then we're applying identity to the first, so it stays 1. But because we're applying an X to the second qubit, it becomes 0. So now we would have successfully created the psi minus states. So the remaining operators we need to apply are these. So HCX, HCX, Z. So we need to apply Z to the 0 states. And finally, we can apply X to the 1 state. Okay, so perfect. So this should give us the results that we're looking for. So I'll just comment these out. So let me see if I can get this circuit to run actually. Let's try that. I hope it does, because actually so Qiskit did an upgrade, and I haven't used the environment I created for the new version in a while. So if you look here, okay, it wasn't even stated here. Okay, this ran successfully. Okay, I hope this works. So let me run this circuit. Let's see if we get anything. Oh, perfect. So as you can see here, we have the Hadamard gates, we have CX, we have Z and X. So what you have here should successfully give us the psi minus state. Okay. I think we measured. Okay, so now we have the sampler, and this is what will help us get the probability distribution of the states. Okay. Okay, so to explain this, okay, okay, let me explain this first, and I will try and fill in the values here. So first of all, what we're trying to do is such that we have our box of chocolates. We have our box of candies, and we said we have vanilla and the raspberry. So we know that we don't know the number of vanilla candies and the number of raspberry candies we have in the box. So one thing we might do, okay, yeah. So for example, now let's say it wasn't two candies we had here. Let's say we had 50 candies, for example. And let's say we have 50 candies, and we had 20 vanilla, 20 raspberry. The thing is that we don't necessarily know how many vanilla and we don't necessarily know how many vanilla and raspberry we have, and we're trying to figure that out. So one thing we can do is that, given the box, we're not looking inside. We just pick one candy and we check to see what it is. So when we pick the first candy, we could see vanilla, for example. Then we return it. Then we pick another one, and we could pick raspberry. And so we're recording all these values. So we pick vanilla once, we pick raspberry, and every time we pick, we replace it, we return it back. So we could do this, let's say 1,000 times, for example, and we could calculate the number of vanilla and raspberry we have. So let's say we did this 1,000 times, and we got vanilla 500 times and raspberry 500 times. We would be like, oh yes, the probability of picking vanilla and raspberry is equal. So we have an equal number of vanilla and raspberry. And if we're even told, let's say there are 50 pieces of candy or chocolate candies in the box, we could be like, yes, maybe, or there's a good chance we have 25 vanilla and 25 raspberries. So the thing about our quantum states is that although I was writing all this out and writing 1/√2 here, 1/√2 here, so these are the amplitudes, and when we square them, we get the actual probabilities. We don't know what these values are necessarily, because we applied a couple of gates here, and these gates could have been changing these values. So we're going to try and run our sampler now to figure out the probability distribution. We're trying to figure out, is there an equal chance of picking raspberry and vanilla? Okay, so Okay, so I'm just going to fill this in. Okay. Okay, so for the sampler, we're going to use the state vector sampler. Okay. For sorry, give me a second. Let me do something. Let me try and run this first and see what I get. Okay. Let me comment this out. Okay, let's try and run this again. Okay, perfect. So as you can see here, we tried picking and replacing the candies in our box, and we did this 1,000 times. So we were able to pick 0, 1. So this is our vanilla flavor, and what we have here, this is the raspberry flavor. So we were able to pick vanilla 484 times and raspberry 516 times. So from this, although it wasn't like a perfect distribution, it's not like we got 500 here and 500 here. But from what we're seeing here, we could be like, yeah, there is a good chance that there's an equal probability of picking vanilla and raspberry. And we could even increase the number of shots. Okay, so as you can see here, we're even closer to a we're even closer to an equal distribution between these two states. Okay. So I think here maybe we can just use, we can introduce our circuit here. We can use our circuit here and just do this. I'm looking for specifics for the task. Okay, so we can just do this. And let's even try and plot the histogram. Yeah, I always forget. I think this is a pie chart. But as you can see here, we have our probability distribution here, and it's almost equal. Okay, so let's move on to the next task. So I don't know if at this point in time there are any questions. Okay, so I think
sorry, please. I really appreciate the way you are taking it, but please, I don't want you to just go deep into this exercise. You can just explain the way you explained the first one. You can just put them through, because they are the one that's supposed to do most of the exercise. So
okay. I should just explain it, and I should not
explain it. Yes,
Okay,
yes.
okay.
Explain it. So solving those one that we've solved, no problem. But please just explain so they can catch up. That's why there are rules. If they get to the I think which of these which states the rules that they need to follow under it.
Okay,
Sorry.
okay, okay. Yeah, no problem.
Okay, that W states. Yeah,
Yeah,
that
I won't touch
W.
anymore. Yeah, I'll just explain. I won't solve it anymore. I'll just explain what
Okay,
we need.
okay. Thank
Yes,
you,
yes.
thank
Yeah,
you.
yeah, yeah, sure. Um, okay, so now we're to create the W states. So we also have okay. So we have the W states here, the W state circuits, and we're to sample one piece of candy from the box, and it contains three candies. So here, these are the three candies: 001, 010, and 001. So okay, so we're to build our circuit such that we get these three states, and they all have an equal probability of being measured. Okay, so um, so these are the three steps. We're to create our circuit with 3 qubits. So in the earlier example, we created our circuit with 2 qubits. Now we're going to make use of 3 qubits. Then we're to perform a rotation. So we perform an RY rotation. So we actually have a gate RY, and we're to it's a single qubit gate. We apply RY to a single qubit. So that's what we're going to do here. We're going to apply the rotation here to a single qubit, and then we make use of a controlled Hadamard gate, such that okay, so the control is qubit 0 and the target is qubit 1. So similar to how we saw the controlled X gates, we have the controlled Hadamard gate here, and qubit 0 is the control. So if qubit 0 has a value of 1, then we're going to apply the Hadamard gate to qubit 1 here. And then we're going to do the same thing. So here we're not applying the controlled X or the controlled NOT gates. And these are the control. So we have the controls and targets specified here for us. And finally, we're going to apply an X gate. Okay, so here, okay, RY was even done for us. So we have RY done here, and we're to do everything else. So all the remaining steps. Okay, we're to initialize the circuit here. So you state your quantum circuits, or you introduce your quantum circuit here, and state the number of qubits that you're going to make use of here, and then we perform all the remaining steps here. So making use of the controlled H, controlled X, and all those other gates, those will be done here. Okay, then we can run our sampler and receive the results and plot the histogram. And we're supposed to get like 3 bars of equal, not necessarily equal, but close to equal lengths. So here they're not equal, but as you can see, the difference is not much. So if you successfully do everything you're supposed to do, you're going to get 3 bars that are of almost equal sizes. Okay, so now we're going to move on to VQE. That's the variational quantum eigensolver. So we're told here that when selecting a piece of candy from our box, the piece often meets our expectations, but sometimes the feeling we get is not our favorite. So what we're going to do is that we're going to make use of a variational quantum eigensolver to assemble a box of chocolates that hopefully meets our expectations. Okay, so we're going to check the expectation values for different combinations of candies. And we're going to use VQE to find the combination with the highest expectation value. Okay, so I'll leave all this for you to go over. But let me try and explain the variational quantum eigensolver first, and then yeah, then we'll proceed. So the variational quantum eigensolver, it works such that we have our circuits, and we might want to, or let me even explain what we're trying to accomplish with the variational quantum eigensolver. Okay, so we have our circuits, and we can apply a couple of gates or operators, and we could apply a couple of gates or operators, and we might be looking for a certain combination. Okay, how will I put this? Our variational quantum eigensolver, the first term we're seeing here is variational, meaning we can change something. It's variational. So we want to vary some quantity or want to vary some value, and we want to find the best possible value from what we're varying that will give us the highest expectation value at the end. Okay, I know that that explanation was a bit, I don't know, tricky, but it's something you could look up. The variational quantum VQE. Okay, so let's move on. So we have 3 pieces of chocolates in our box, and each piece can either have vanilla or raspberry. So the user likes vanilla but dislikes raspberry. Okay, so if the user or the person picking from the box was to pick vanilla, he gains 1 point. But if you were to pick raspberry, you get -1. And so we're to create an operator now to model this. And to do that, we're going to make use of 3 poly operators and sum them. Okay, so we're going to create our operator such that if it's a vanilla center, you get a point. But if it's a raspberry center, a point is taken from you. So you could think of this as this is what will, okay, so this is our cost function. And this is what will enable us to get the highest expectation value for something. So we're going to vary our inputs, and we want to get the highest possible point. So we want to vary our inputs such that we keep getting points for introducing vanilla as against when we introduce raspberry, and points are deducted from us. So we're going to vary something that's from the variational that you see here. And what we're interested in is introducing vanilla and not introducing raspberry. because this takes away points from us. Okay, so now we're going to set up our variational quantum. So we're going to implement the algorithm here. So it's actually a hybrid algorithm. We don't strictly utilize a quantum computer for this. We make use of a quantum and a classical computer. And these are a couple of applications. So we could use this for chemistry, optimization problems, and stuff along those lines. So what we're going to do is that in our quantum circuits, this is where we vary something. So we vary something and we get our expectation value, and then we use classical techniques to check if it's the highest possible value that we could have gotten. And if it's not, we're going to send back new values for our circuits. So whatever we're varying, whatever parameter that we're varying, we're going to send new values for that parameter. And then we'll calculate and see if we get suitable expectation values. And so we'll keep repeating that. So the classical side, it's more about checking to see if we've gotten the best possible value. So this helps us check if we've scored the most possible points for choosing vanilla. And if it's not, we'll send in new values to our quantum circuits, and then we'll calculate again. When we've calculated, we'll check we'll send to our classical circuits, and it will check to see if we've gotten the highest possible value. And if not, we just keep repeating the loop until we stop somewhere. So when thinking of chemistry and okay, let me say optimization, for example. In terms of optimization, let's say it was even something along the lines of investing in like stocks that will yield the highest possible returns. So one thing you could do is so with our variational parameters here, we pick a couple of stocks, and then we calculate the expectation value and pass it to the classical circuit. So in the classical circuit, we'll check to see is it the highest possible yield we could have gotten from our combination. And if it's not, we'll send back like new values for our quantum circuits, and we just continue the loop until we get the highest possible output that we could get. So our VQE, so we have the parameterized parts. So that's our ansatz. That's our ansatz. And we're trying to solve for the ground state of the Hamiltonian So I think the ground state here will give us the best possible results. So we're going to set up our okay, so we'll set up our Hamiltonian, and the Hamiltonian is the energy, and okay. Okay, so we set up the variational part of our circuit, we run it, and then we introduce our classical optimizer to get the best possible value. Okay, so this is the parameterized part of our circuit. So we're going to make use of the two local circuits here. And okay, so this is a common circuit used for a lot of variational algorithms and even for quantum machine learning. So it's a parameterized circuit with alternating rotation layers. So this is the variational part. We vary how much we're going to rotate by, because we've seen gates such as the RY and RZ gates. And this is the variational part of our circuit. This is where we determine like how much rotation that we're going to introduce. And then we also have the entangling layers. Okay, so we're told to make use of CZ gates for our entangling layers. Okay, so we're to get all our parameters right and introduce our answers. So our answers, as I said, this is the variational part of our circuit. Okay, then finally here, we're meant to transpile. We're meant to transpile our circuits. So fake Sherbrooke here, it's a simulator, but it helps us simulate the 127 qubit backend. Okay. So when we transpile our circuits, it helps us optimize the circuits for the specific backend. So that's what we're going to do here. Or to optimize our circuit to run on the fake Sherbrooke. Because our backend has a specific architecture, and the instructions we pass, so there are certain constraints for the device, like the types of gates it wants to run, and in terms of the qubit connectivity, that is for the multi-qubit gates, like the CZ gates that we're going to apply. We have to transpile our circuit such that it's sending the right instructions for a specific backend. Okay, so this is where we define our cost function. Okay, so we have a scalar cost function, and then we're to minimize it. So we're looking for the lowest possible energy. So as I said earlier, the Hamiltonian is our energy, and we're looking for the lowest possible energy states. Okay, so this is where we define our cost function. So even from the callbacks, even from the callback dictionary we have here, we're storing a couple of useful things, like the history, the number of iterations, previous results we've gotten. And then we have a classical optimizer. So if you're even like conversant with machine learning, we have a process here like similar to machine learning. And okay, so we have our classical optimizer, as I said earlier. So this is what helps us like figure out the best, or this will help us minimize the cost function. Okay, so here we're going to set like the initial values. We set initial values, and then we run our circuits. The classical optimizer will find like a better possible input you could introduce, and it goes on and on until we find the best possible value. Okay, so we have the new estimator interface here from Qiskit, and for a single circuits. You can specify multiple observables, parameters. Um, we also have the primitives here that help out with like error mitigation and suppression. Okay, and we've spoken about the sampler. Okay. So I think that's pretty much like the core of it. So this is pretty much about like running our circuits and yeah, we have a couple of runtime services here that are useful. Okay, so I think that's pretty much it for this notebook. Okay. I actually have to go soon, but I don't know. Are there any questions at this point in time? Okay. So hello, Mr. Shagun. Am I audible? Can you guys hear me?
Yeah, we can hear you.
Okay. So I think that's all on my end. So thank you. Good luck with the challenge. All the best. So most of these things is just to keep at it. Just trial and error, regardless of if you fully understand what's going on. Just like make a few tweaks here. Try it out. If you could even ask for like directions or advice, or sometimes people like post stuff. Usually like let's say Qiskit's Slack channel, um, like tips and stuff like that. So you just make a few changes here and there, test it out, see if it works. Go back, look for better or more direction, try again, and yeah. So like kind of like the VQ circuit, you just keep iterating until you get the right answer. Okay. Yes. I think someone has a question.
Actually, do we need to submit this exercise book?
Sorry, I don't know what you mean by segments.
Means the exercise book that are shown today, we need to perform them and need to submit those thing in our exercise.
Yes, so you're supposed to um solve the exercises and submit the solutions to Mr. Shegun, if I'm right. Yeah, I think that's what you're supposed to do. You're supposed to solve the exercises and submit the solutions to Shegun. So I think if you do that, I think it's not just today. Like there are a couple of notebooks, but if you do all the notebooks and get them all right, then Qiskit will give you the certificates.
Okay, and the point of contact is Shagun, correct?
Yes, yes.
Okay.
Sorry,
Thank you.
sorry. About the certificates. We are going to the one given to us is going to be given to us just for the Qiskit if for first. So if you participate, you have a certificate. If you do the challenge, the exercise you have, and you do it properly well, you have a certificate for that as well. So actually, you are free to. Some people enter into my DM, chat me, ask me question how to install these. They're having issue with this, they're having issue with that. So from there, I put them through and I explain how they can go through it for them. So if you have any issue, you can just chat me up. You can chat me up, and from there I can explain to you. But today I will drop the notebook for the exercise. Actually, this exercise is much, but I can just put some little tips on how to go about it on the group for anybody to access it. So just try. And also the notes I dropped the documentation on page. You can just go through the documentation also. It's good to know how to make use of documentation so that you can for other advanced process so that you can able to know how to read the documentation to solve your problem, to solve any issue that you have. So and is there any other questions, sir? Hello, is there
No,
any question?
no,
Okay,
no, no.
okay, okay. Thank you very much for today. We really appreciate you guys' time. Actually, most of us are still at work, so you can see many of them are going off. Thank you so much, Mr. Kenneth, Mr. My other colleagues. Thank you so much, and thank you for those who participate in this. We really appreciate. Please, there are a lot of benefits in this. You may be looking at it as it's not going to benefit you, but if you put your time and effort, you will gain more from it. Thank you so much. Please, by tomorrow, we are joining again for tomorrow for this last section for the notebook, and the final section will be on 27. We are going to give out the certificate and put us through the necessary things and tell us which um parts or which areas you can specialize on. So thank you so much. Have a wonderful day. Thank you.